Welcome to Lead Programmer. Today we are going to look at the question validate stack sequences. So we have two integer arrays pushed and popped. Each of them have distinct values. We want to return true if these arrays would have been a result of a sequence of push and pop operations on an initially empty stack. So what we mean over here is, let's look at the first example. So in the first example, we have a pushed and popped array. Uh, let's say we had an initially empty stack. We want to push a few elements. Okay, so we push a 1, we push a 2, we push a 3, we push a 4. But hold on, we also have a popped array. So one sort of operation would have been, okay, so we pushed till 4 and then we probably pop 4 to satisfy the popped array. So we pop 4 and then we cannot pop 5 yet because 5 isn't present in the stack. So we push 5. We are over here so far. So we push 5. So 5 goes in. And then we see, oh, we can pop 5. So we pop 5. Next we have 3. So we see, okay, we can pop 3. So we pop 3. We can also pop 2 and we can also pop 1. So at the end we see the stack is empty. We have gone through the entire pushed and popped array. Hence it's possible. Hence the answer is true. Let's look at a case which is not possible. Let's look at example 2. So we have pushed and popped arrays. So we again keep pushing. So we push 1, we push 2, we push 3, we push 4. We observe that the popped array begins with 4. And we have already pushed 4, so we can pop it. So at this stage we pop 4. We observe a 3 over here, so we can pop the 3 since it's the topmost element. Then we observe a 5. Can we pop 5 yet? No, we cannot. So we go back to the pushed array. We are at 5, so we can push 5. So we do that over here. And then we come back to the popped array. We notice that, okay, we can pop the 5. So we pop the 5. Now the next one is 1. Can we pop 1? No, we cannot pop 1 yet. We cannot pop 1 before we pop 2. So this gives us a non-empty stack at the end. Where we get stuck, we cannot pop 1 because 1 is not the topmost element of the stack. Hence the answer is false. So as we went through the example, you might have noticed that we keep pushing the elements in the stack. So we keep pushing the elements in the stack until we are in a position to pop an element. So in the first example, we kept pushing till 4. We noticed that 4 is the latest element. So we have a pointer to keep track of the position in popped. So the pointer is currently at 4. As soon as we insert 4, we know we can pop it because 4 our pointer is present at 4. So well and good, we pop 4. Next we see we have a 5 in the popped array, but we cannot pop 5 yet because 5 is still not pushed. So in that case, we go back to the pushed array and then we push a 5 and then we proceed that way. So one way to solve this problem is, you guessed it, using a stack. So we essentially got the idea. We keep pushing to the stack until the element we pushed is equal to the element our pointer points to in the popped array. And once we go to the popped array, we try to keep popping elements till possible. Once it's not till it's not possible, so till we reach a stage that it's not possible to pop the elements, we go back to the pushed array and we keep pushing until we pop. Let's look at the code to understand this better. So we have a stack. We have a pointer on the pushed array. We have a pointer on the popped array. So we keep iterating through the pushed array and we keep inserting the elements to the stack. Now once we do that, we check, can we pop the element. So we keep going through the popped array, and we see if the last element is equal to the element uh, pointed to in by our pointer in the popped array. If it is equal, then we pop from the stack. So we had popped over here, and we just increment the counter there. Else, here we append to the stack because we had removed from the stack here. So if the pop operation is not done, so we popped here and we appended here. That means effectively no change had been made. On the other hand, in this scenario, we were allowed to pop, so we made no change because we had already popped here. We just incremented our pointer, which points to elements in the popped array. So in the else case, where the pop operation couldn't be done, if we reach that scenario, we just break. And we have a while stack because we don't want to pop if the stack is empty. So at max, we can go till the stack is empty. And here we just update the push I pointer. So at the end, we return not stack, because recall, if stack would return true, if the stack is not empty, and if not stack would return true if the stack is empty. So at the end, we want the stack to be empty, because you might have noticed in the second example, the stack will not be empty, because at this stage, we would reach the point where we cannot pop further and we cannot insert any elements. So the stack would have so the stack would have 1 and 2 elements remaining. So that's why we want to return true only if the stack is empty. And as you might have guessed, the time complexity of this solution is the big O of n, because we go through the array at most once. The space complexity would also be the big O of n, because we use a stack, and that stack can potentially have all the elements in the array. And n is the length of the pushed and popped array, and as given in the constraints, the pushed and popped array have the same length. Hope you found this helpful. Please subscribe to the channel. Thank you.